And thank you for giving me the opportunity to speak at this conference. So the topic of this talk is the two-body problem on a sphere in the presence of a magnetic field, and it's the subject of my joint work with my supervisor, Dr. James Nataliya. And it is a generalization on a quite well-known Kepler problem of gravitational interaction of two bodies. The first interaction of this generalization is due to Borisov, Mamayev, Nataliya, and Garcia Naranjes. I'm sorry if I didn't pronounce that quite correctly. And what they did is, instead of placing the two bodies in space or in a plane, as in the classical formulation of the problem, they placed the two bodies on the surface of a unit sphere. And what we have done is we have thrown the magnetic field into the mix. So first, let's recall some elementary facts from physics. So we suppose that a particle of charge E and mass mu is located somewhere in R3. And it is, additionally, we have a magnetic vector field B and electric vector field E. And then its motion is governed by Newton's second law with Lorentz force on the right-hand side, given here. And as for the properties of B, B must be the divergence-free vector field because of Maxwell's law. Since we're in R3, we can apply hot star to B as a vector field and obtain a two-form given by this formula here, comprised of the elements of B, and stating that Maxwell's law is equivalent to stating that B is a closed two-form. Now, suppose instead of one charged non-relativistic particle, we have two charged non-relativistic particles in three-dimensional space. And if, so their respective masses are μi, their respective charges are ei, coordinate vectors qi, and physical momenta pi. If the interaction potential between these particles is given by some function v of q1 and q2, then we have these equations of motion, which can be obtained from Newton's second law. These equations happen to be Hamiltonian if the Hamiltonian is given by this function here. The phase space is going to be, apologies. The phase space is going to be two copies of cotangent bundle of R3. And the symplectic form is given by this 12 by 12 matrix omega, where this Gothic B is a 3 by 3 schizommetric matrix comprised out of elements of B. It is obviously schizommetric, it is obviously non-degenerate. And this is where the fact that B is a closed two-form comes into play, because we need B to be a closed form for omega to be a closed form in turn, to be a symplectic form. Now, all the previous works known to us dedicated to Hamiltonian approach to studying of motion of two charged particles have been set up in R3 or on the plane maybe. And the magnetic vector field B has always been assumed to be vertical and have uniform strength. And the symmetry group of this system would consist of rotations and translations, and rotations around vertical axis only. So we decided that we want to have SO3 as the symmetry group. And to this end, we place our two particles on the surface of a unit sphere and assume that our magnetic vector field B is of uniform strength and orthogonal to the surface of the sphere. So we have a picture something like this, decidedly not coronavirus-like picture. And additionally, now we take function V to be a function of the norm of Q1 minus Q2 and demand that its derivative is non-zero everywhere. The configuration space of our new problem is going to be two copies of S2 minus S delta, where delta is the union of the diagonal subset of S2 times S2 and the subset of antipodal points. So we prohibit our particles from colliding, and we prohibit them from being on the opposite points of the sphere at any point in time. So this letter is, we denote our configuration space by letter Q, and cotangent bundle of Q can be embedded in two copies of cotangent bundle of R3. So our Hamiltonian system can be pulled back to T star Q, and we get a Hamiltonian system that describes the motion of two particles on a sphere. Since we have quite obviously succeeded in making it SO3 symmetrical, we have an equivariant momentum map phi given by this formula and written here through Q and P for convenience and brevity. Here we fall, and now what we want to do is to get rid of SO3 symmetry immediately. So perform a reduction, and to this end, we employ the method used by Borisov and Mamayev et al. In their paper, and represent any matrix in SO3 through three Euler angles, theta, phi, and psi, and any element of its Lie algebra is a schizometric matrix whose elements double as the angular velocity of the system. Additionally, we introduce a new variable q, which is going to be the angle between the coordinate vectors of the particles, and q dot as its rate of change. And on the unit sphere, q will double as the geodesic distance between the particles. Now, the idea of the method is that we can set two default positions of the particles, so say 0, 0, minus 1, and 0 cosine q minus cosine q, so that the particles are separated by the geodesic distance q. And then, to reach any configuration of the particle pair, the only thing we need to do is to rotate them by some element of SO3. And thus, we can parameterize our tangent bundle of our phase space TQ through Ti times TSO3, where I is the interval where Q lives, given by these explicit formulae. The only hitch is that for Hamiltonian formulation, we need a cotangent bundle rather than the tangent bundle. And usually to transfer from the tangent bundle of the phase space to a cotangent one, we would use a Lagrangian. But since our B does not have a vector potential, so we don't have a Lagrangian essentially. And for transferring to a cotangent bundle, we need to introduce a new set of coordinates through a kinetic energy of the system. So we take P to be dt over q dot and mi's dt over d omega i's. We can rewrite the Hamiltonian. So we have a new set of 8 variables, theta, phi, psi, mi's, p, and q. And in those new variables, we can rewrite the Hamiltonian, we can rewrite our symplectic form, and we can write Hamiltonian equations, 8 of them, which are a bit too long to put on the slides. But the idea is that the last 5 of them in mi's, p, and q form an independent system, which we will refer to as our reduced system. And we will call them our reduced variables. The Hamiltonian, since it's rotationally invariant, will have this form in our new reduced variables. The non-zero Poisson brackets in the reduced variables will look like this. And since the Poisson structure in our reduced variables is obviously degenerate, it will have a Casimir function C given by this, which coincides with the square of the norm of the momentum band. And a slight side note, which I will talk if I have time, is that if we set B equal to 0, then as the limiting case for B equals 0, we have the gravitational two-body problem on the surface of the sphere. The Hamiltonian equations in reduced variables look like this, which is rather an unpleasant bunch. And what we want to find are the relative equilibria of this system, which are rigid body-like rotations of the particle pair around the fixed axis. Since we have taken out the SO3 action, they will coincide with the zeros of this system. So we are hunting down the zeros of the system. In general, they're very hard to locate, and that's actually not true, that's impossible, but we can still say something. So for every q from 0 to pi, we have at least one relative equilibrium. So there exists a configuration where particles are separated by the distance q and are rotating around some fixed axis. But if and only if this expression, this long expression in v, b, mu's, and e's is greater or equal to 0, does a relative equilibrium exist for q equaling pi over 2? Now, we want to make this problem more tackleable, and we assign a concrete value to the potential v of q. We take it to be cotangent of q, and say that we just assign numerical values to the masses and the charges of the particle. Namely, we take them all to be 1, and namely say that this case is the case of identical particles. And the equations look significantly less threatening now. So they have this form, and in fact, we can solve them now, which is good news. And here is the first pair of the solutions, which we'll refer to as type 1 relative equilibrium. And everything I say about existence and further on stability of equilibria, I will formulate in terms of B and Q. So the strength of the magnetic field and the angle. And as you can see, type 1 relative equilibria exist for almost all values of B and Q, because this expression here is always positive 1, except for Q equaling pi over 2, because the denominator here is going to be 0. The other pair and the second pair of the solutions is going to be type 2 relative equilibrium, which is slightly more capricious because they don't exist for all values of B and Q, and if and only if this expression here is greater than 0. So type 1 relative equilibria exist if and only if on the QB plane, the points are above this curve, which we'll refer to as the bifurcation curve. And here, strictly above it, we will have two different relative equilibria of type 2. But on the bifurcation curve itself, these two solutions will coincide. So they will merge, and I'm using this term quite loosely, into one relative equilibrium. The minimal value of this that this function assumes is that Q equaling 2 pi over 3, with B being 4/3 3 to the power of 1/4. And I will mention this quite a few times in the future. So the first thing we want to do is we want to draw the energy Casimir map. So we have the bigger picture on the right, on the left, and we have the close-up of this on the right. And it was drawn for a concrete value of B equaling 2.5. First, let's restrict our attention to this yellow-green, what I was told was not quite yellow-green, loop on the bottom here. And it is formed by energy Casimir values of relative equilibrium of type 2. And it is a closed loop, as you can see here in the close-up. And yellow part of this loop corresponds to one relative equilibrium of type 2, and the green part corresponds to the second relative equilibrium of type 2. And as you can see here, the green and the yellow line, parts of the line merge together, and that is exactly the value of Q, where the line B equaling 2.5 intersects our bifurcation curve. And I'm going backwards, sorry. And the same happens somewhere around here. So this is exactly that one merged relative equilibrium I was talking about. Now, relative equilibria of type 1 exhibit quite a suspicious behavior here, because all the values of Casimir and Hamiltonian for all values of Q are the same for both of them. And as it turns out, and as a little computation shows, that they are in fact one relative equilibrium in disguise. Because if we change the places of the particles, which in this case is the symmetry of the system, then this maps one relative equilibrium of type 1 onto the other. So we do not distinguish between them. Now, this very, very long theorem basically assigns the number of relative equilibria to every point in the BQ plane. There are many cases, but I won't go into the details. So suppose the value of B is quite small, and for us small is less than this critical number here. So if you will imagine the horizontal line here, and it does not intersect the bifurcation curve. So for every value of Q with B less than this number, we have one relative equilibrium except for pi over 2. Pi over 2 does not have any relative equilibrium. And if B is big, which in our books is greater than 2, so the line B's constant lies somewhere here, then to the left of the intersection, we have one relative equilibrium. To the right of this intersection, we have one relative equilibrium for every Q, 2 on the intersection points, 3 everywhere in between, but at pi over 2, we will have 2 relative equilibria. And the rest of the statements are just the cases. So knowing the explicit solutions of our system, we can go back from mi's to omega i's, which are, again, angular velocity of the system, and we can restore the motion of our particle pair. So for relative equilibria of type 1, we have these pictures. They are going to be both obtuse and acute configurations, so meaning that the angle between the particle pair could be either obtuse or acute. And they're going to be asymmetrical in the sense that these two angles formed by the coordinate vectors of the particles and the axis of rotation are different. Relative equilibria of type 2, on the other hand, are the so-called isosceles configurations, meaning that these two angles are going to be the same. And another interesting property is that one geometrical configuration could be occupied by a system in with two different states of energy, which obviously results in the different rotation speeds. Now, having talked about existence, we want to talk about stability of relative equilibria. And when I say stability, for now, what I will mean is linear stability, which was calculated in the most brutal, time-consuming way of differentiating our system of equations, plugging in the relative equilibrium, and finding the eigenvalues. For relative equilibria of type 2, everything had to be done numerically because of the complexity of the resulting equations. So we get the following pictures, assuming that the values of B are reasonably small. So for the first relative equilibrium of type 2, we will have this. The curve on the bottom is our bifurcation curve. In darker lavender color, we will have the area of stability. And this tiny sliver here is where this relative equilibrium will be linearly unstable. For the second relative equilibrium of type 2, the picture will look like this. So the area of instability will be noticeably bigger, given in lighter purple here. And this will be the area of stability. Drawing them both on the same picture will get this. So this will be the area where both of them will be stable. Here we will have one unstable, one stable, and two will be unstable here. As for one coinciding relative equilibrium on the bifurcation curve, it will be unstable when Q lies from 0 to 2 pi over 3, and it will be stable when Q lies from 2 pi over 3 to pi. And another noteworthy thing is that both of these lines here, so the darker purple and the greenish one, separate from the bifurcation curve at Q equal to pi over 3. So this line is pressing very, very, very tightly into the bifurcation curve. Now, the last but not the least, I would like to talk about our favorite point, which is the bottom point of the bifurcation curve, and determine its stability. We had to employ numerics here as well, because this is a very, very, very degenerate relative equilibrium, since it's separating so many areas from stabilities, from so many areas of instability. And on the picture on the left here, in purple, you can see the trajectory of the system at the relative equilibrium drawn through three Euler angles, theta, phi, and psi. And the thin line in red is the slightly perturbed trajectory, separating from it quite dramatically. This picture on the right is perhaps slightly more illustrative. So in there is the function of the distance between the perturbed and unperturbed solution of time when the initial perturbation was 5 times 10 to the power of minus 3. So clearly this relative equilibrium is unstable, as physical intuition told us from the get-go. Now, stability of relative equilibria of type 1 is slightly easier to determine. So they're much more well-behaved in this respect. Again, the area of stability here on the BQ plane is given is in darker purple, and the area of instability is in lighter purple. And now the curve separating from the stability from instability can be found analytically, in fact. So this is this, given by this formula, and it meets the horizontal axis of Q equaling pi over 2. We want to revisit the momentum map briefly and assign the physical value to the cusps of this momentum map. They are the points that separate the area of stability of the solutions from instability. And another thing of notice is that relative equilibria of type 2 are Lyapunov stable when they're stable. And these signatures here are these quadruples of pluses and minuses are the signatures of the Hessian at the respective parts of the curves. And here you can, this is a simplified diagram, but here you can very well see that two unstable solutions merge into one unstable, and two stable solutions merge into one stable. seeing as we have done such a concrete small case, we want to squeeze out of it as much for free as we can. And there is another case that can be easily obtained from ours, and that is the case of equal masses and opposite charges. And the equations for this case can be obtained from our equations by a simple change of coordinates that does not affect the existence of relative equilibria. And as for stability, everything we have to do is to flip the pictures that I have shown you with respect to q equaling pi over 2. And that automatically gives us the areas of instability and stability for opposite charges. However, it is only to be expected that when we try to restore the motion in this case, it will be quite dramatically different, because instead of a repelling potential, we now have an attracting one. So two relative equilibria swap places in a certain sense in this case. Relative equilibria of type 1 now will have the axis of rotation in between the particle pair, but they will still retain their asymmetricity. And relative equilibria of type 2 still remain symmetric configurations with two different energy states related to one geometric. But now the axis of rotation will lie to the side of the particle pair. And the last thing that I wanted to cover, which I think I have a little bit of time for that, is how the gravitational two-body problem is approximated by our magnetic one. As I have mentioned, if we set b would be equal to 0, then our problem basically turns into the gravitational problem of two identical bodies with a repelling potential. And almost all of the relative equilibria of this problem are approximated by relative equilibria in our problem. And they have to be relative equilibria of type 1 that approximate them, right? Because relative equilibria of type 2 don't exist when the values of b are very small. But there is one interesting family of right-angled relative equilibria, which is not straightforward where it comes from. So for the two identical bodies with gravitational repelling potential, we have a family of right-angled relative equilibria parametrized by the angle q between the first body and the axis of rotation. But relative equilibria of type 1 do not exist when q is equal to pi over 2. So the question is, where do they come from? From our problem. When b is equal to 0, all of our system of equations is reduced to one single equation, and 2 and 3 is equal to 1. And setting b equal to 0 and taking the Taylor series of explicit formulae for type 1 relative equilibria gives us these two expressions, which obviously multiply to 1. So there are some instances of right-angled relative equilibrium. However, obviously these are not all. So where did the rest come from? So I don't want to go into the details because I don't have time, but the idea is that as m2, m3 as a function of q with a parameter b do not uniformly converge in the epsilon neighborhood of pi over 2 with b tending to 0. And we do what we always do when we can't exchange the order of the limits. We take different approaches to this. So we take b to be a function of q and demand that it is 0 at pi over 2 and that its first derivative of pi over 2 is number a. And for the Taylor series of m2 and 3 now, we have these two expressions, which obviously multiply to 1. And now we have all the instances of relative equilibria obtained from our problem. Thank you very much for your attention.
Okay. Thank you very much, Alex.